Hello and welcome everybody. Sorry I'm not there today, but today we're going to go ahead and we're going to move forward with the start of our next unit. Our next unit is all about exponents, so please make sure you have a note packet. If you didn't grab one when you walked in, make sure you go back and grab one. We're going to talk about exponent rules here kind of the next 4 days. Exponent rules, these are things that you've seen before. I know they cover them quite a bit in 8th grade math. However, it's an important topic that warrants some review. So hopefully this should feel at least somewhat familiar to you today as we are going through some of these rules. And again, today we're going to focus on just 2 rules. We're going to talk about what happens when we have exponents of 0 and what happens when we have negative exponents. So let's go ahead and get started. So we're going to start by looking at this table here, and we're just going to notice some patterns that are happening just to better understand exponents. So if we work on filling out this table on the left, the first thing we see is 2 to the 4th power, which again, 2 to the 4th, remember that means we got to take 2 times itself 4 times. So 2 times 2 is 4, times 2 is 8, times 2 is 16. Right? It's not 2 times 4, it's 2 times itself 4 times. Next, we want to figure out 2 to the 3rd, so that's 2 times 2 times 2, which will give us 8. 2 to the 2nd, well, that's 4, right? 2 times 2. 2 to the 1st, 2 times itself 1 time, that would just be 2. Now we get to this 0, right? We might be thinking, ooh, what is 2 to the 0? Well, let's think about what we've been seeing in our table, right? As our powers or as our exponents have been decreasing by 1, right? We go 2 to the 4th, 2 to the 3rd, 2 to the 2nd. What do we notice between our values that we've been getting out? Hopefully you see a pattern of each time, right, we decrease our power by 1, we are just dividing by our big number, which remember we call that the base. We're just dividing by 2 each time, right? 8 divided by 2 is 4. 4 divided by 2 is 2. So we can answer this first question here. What happens each time the exponent decreases by 1? Well, we're just dividing by 2. By knowing this fact, we can go ahead and fill out the rest of the table. Well, if I keep this pattern going, I think, well, what's 2 divided by 2? Well, that would give me 1. So 2 to the 0 is 1. 2 to the negative first, again, I got to keep going with my pattern. If I divide by 2, 1 divided by 2 would just be 1/2. Again, if I keep going, if I keep dividing by 2, half of a half is 1/4. So it says what happens, it says in each column, but really in just this one column, when the exponent is 0. Well, we found that when the exponent is 0, we got an answer of 1. And we're actually going to find out that's going to be our rule for today. Anytime we have a number raised to the power of 0, we are going to go ahead and get 1. The other question they're asking us to examine, we're going to do one more example kind of looking at patterns here. But they said, notice how are 2 to the 2nd, which is right here, and 2 to the negative 2nd similar? Well, if we notice 2 to the 2nd is 4, 2 to the negative 2nd is 1/4. So we will notice, and we'll talk about this a little bit more later, but they are reciprocals of each other, right? Their answers are. They are reciprocals. We had 4 and 1/4. Again, we are going to use this to help us a little bit later with our negative exponents. Again, we just wanted to do this example just so we could see some different patterns that are happening. So let's do another one where we kind of look at patterns. So it says consider 3 to the 3rd, 3 to the 2nd, 3 to the 1st. So let's think about what these values are. 3 to the 3rd, again, that's 3 times 3 times 3. Well, 3 times 3 is 9, times 3 is 27, so 3 to the 3rd is 27. 3 to the 2nd, that's 9. 3 to the 1st, 3 times itself 1 time is 3. So it says essentially decreasing the exponent by 1 is the same thing as dividing by, and in this case, for this example, it looks like, how do I get from 27 to 9, 9 to 3? I'm just dividing by 3. So essentially by decreasing the exponent by 1 is the same as dividing by, we're going to say the base, which is the big number, which in this particular example, it's the same as dividing by 3. Again, if we know this pattern, we can keep going, right? If I want to get 3 to the 0 power, well, I just keep going with dividing by 3. 3 divided by 3 would give me 1. Divide by 3 again. 1 divided by 3 is 1/3. And again, we're coming up on our first rule here. We notice anything, or so far, anything that we've raised to the 0 power has been 1. Before we talk about that first rule, I just want to make sure we're all on the same page for vocab here. Maybe I should have done this first. But these are things we've talked about before, but I just want to make sure we're on the same page. The little number, right? We have kind of two words that I generally use interchangeably for it. That little number, we either call it the exponent, or you'll probably hear me call it the power, right? 2 raised to the power of 4, 2 to the 4th exponent, 4th power, 4 is the exponent. The other one, and again, we've talked about this before, that 2, the big number, that's the bass. Remember I made that analogy to music before, right? The bass is the big instrument in music. It's the big number here. 2 is the bass. And this entire thing, and this is what we're going to be working with, this is called an exponential expression. Right, not an equation because there's no equal sign. It's an exponential expression. Again, just a little vocab just to make sure we're all on the same page. So here's our first rule for this unit. If we have a number raised to the power of 0, that answer is always going to be 1. Always going to be 1. The exception is if it is 0 raised to the 0 power. If we have 0 raised to the 0 power, that's the only time something raised to the 0 power is not going to be 1. It's actually going to be undefined. And the reason being is, and I can talk about this more when I'm back, but if we have 0 to the first power, right, 0 times itself 1 time is 0. And if I want to get to 0 to the 0 power, if we think about our patterns like we were doing before, we said, well, we have to divide by the base. Well, we know we cannot divide by 0, right? So 0 divided by 0, that's, if we put that in our calculator, we get an error, right? So that's undefined. So any number raised to the 0 power is always going to be 1, with the exception of 0. So if we see questions like this on a quiz or a test, we should be super happy. Because if we remember the 0 exponent rule, these go pretty quick, right? What's 5 to the 0 power? 1. What's negative 2 to the 0 power? 1. What's 1/9 to the 0 power? 1. If I asked you what's 1 million raised to the 0 power, we'd also say 1. The only one we got to keep track of is 0 to the 0. That's where we'd have to say undefined. So let's go ahead and check our understanding here. So it says evaluate the expression 2 to the 3rd times 2 to the 0. So this goes back to PEMDAS, right? PEMDAS says we got to figure out our exponents before we deal with the multiplication. So 2 to the 3rd, that's 2 times 2 times 2. So that's going to give me 8 times, I also have to evaluate this exponent here, 2 to the 0. We just said anything to the 0 power is 1. So we get 8 times 1, which gives us, oops, circled the wrong one, gives us 8. Again, just using PEMDAS to simplify. Again, our first rule, anything raised to the 0 power is 1, with the exception of 0. And our second rule here for today is we're now going to talk about negative exponents. So if we remember back from the beginning, right, if we had, we looked at 2 to the second, 2 to the negative second, right? 2 to the second, we said was 4. This was what we did way back at the beginning. And we said 2 to the negative second was 1 over 4. Our negative exponent rule says if we have a negative exponent, we must make it positive before we evaluate. And we make it positive by moving it to the opposite side of the fraction. So like in this example here in the yellow box, right, a to the negative n, right, we have a negative exponent. We can't evaluate it as a negative exponent. We must make it positive. I know you may be thinking, well, this isn't a fraction. Well, we can make it a fraction, right? We can put it over 1. Before I can evaluate, I have to make my exponent positive. So I need to do that by moving it to the denominator, which is what I did over here, right? I moved a to the n to the denominator, made my exponent positive. I didn't have anything left on the numerator, so that's why we just put a 1 there. When I learned negative exponents, my teacher always talked about siblings, right? If you have a sibling at home, and let's say you have 2 floors in your house or wherever you're at, and let's say you are being negative upstairs, maybe your mom or dad or whoever might send you downstairs, right, to become positive. The same is true if we have a negative exponent on the denominator of our fraction. In order to evaluate it and make it positive, we'd have to move it to the top of the fraction or to the numerator to make it positive. So again, I always think about kind of that sibling analogy, right? If you're being negative in the basement, you might have to go upstairs to the top or the numerator to become positive, have an attitude adjustment. Same thing with kind of negative exponents. We have to move them around to make them positive. So that's why 2 to the negative second was 1 over 4, because 2 had a negative exponent, right? So in order to evaluate, we have to move that to the bottom of a fraction, right? Because right now it's like on the numerator. So we bring it down, and when we bring it down, the exponent becomes positive. Again, nothing's left up top, so we assume it's a 1. 1 over 2 squared is 1/4. So that is our negative exponent rule. Whenever we see negative exponents, we have to make them positive, and we make them positive by moving them to the opposite side of the fraction that they're currently on. So let's go ahead and look at some examples here. We're not going to do this slide here. We kind of already gone through a few examples of looking at patterns. But let's go ahead and look at this one. So here's some examples of some problems you might see. First one, negative 8 to the 0. Hopefully everyone's thinking, ooh, negative 8 to the 0, anything to the 0 power, that is 1, right? That's a nice, easy one. 4 to the negative second. A lot of times I see students say, well, the answer is negative 16, but that's not the rule for negative exponents. If you plugged it into your calculator would not say negative 16. It's going to give you some sort of decimal here. Because we have a negative exponent, we have to make it positive. Remember, if we want to make it positive, we have to move it to the opposite side of the fraction. Currently, it's on the numerator, so that means I have to move it to the denominator, the 4, and the power it's raised to, but since it was a negative 2, it becomes a positive 2 when I move it down. Nothing left on the numerator because I moved the 4 down, so that leaves me with 1 there. So 1 over 4 squared, 4 squared is 16. We'll come back to the middle one. I want to talk about that in a second. 73 to the 0, hopefully everyone's saying again, ooh, 1, right? That's a nice one. 13 to the negative second, again, we can't evaluate as is. We have to make this exponent positive. So I'm going to move it to the denominator. So it's going to be 13 to the second power. Again, nothing left on top. So we're going to put a 1 there as a placeholder. 13 squared is going to give us 1 over 169. This middle one is kind of another rule or little trick you can use with exponents, right? If I have 1/2 raised to the negative 1 power, basically that's saying, well, I have to raise 1 to the negative first and 2 to the negative first power, right? So technically to evaluate here, I would have to move the 1 to the denominator, and I'd have to move the 2 to the first to the numerator, right? So it'd give me 2 to the first if I'm working this way. Sorry, that's kind of weird. 2 to the first over 1 to the first, right? They both have to move to get their positive exponents. One little trick is if I have a fraction raised to a negative exponent, I can go ahead and just replace it as the reciprocal of that fraction raised to the positive exponent. Because that's basically what we just did over here. It's just doing it maybe in less steps. So it would give me 2 divided by 1 is just 2. 2 to the first is 2. All right. So before we get into a few more examples, when simplifying exponential expressions, no 0 exponents can remain. If we have exponents that are 0, that means we are not done simplifying. We have more work to do. You are also not done simplifying until all exponents are positive. If we have 0 exponents or negative exponents, we are not done simplifying. So here's how the problems are going to look today. A little bit more complex than maybe the basic ones we were doing at the beginning. It says rewrite the following expressions using positive exponents, or it could have just said just simplify here. So how I attack this is I go through and I look at each term and I think about, do they have a negative exponent or not? So the first term I see is 5, right? It doesn't show that 5 has an exponent, but we know there's an imaginary 1 there, right? 5 to the first. So that has a positive exponent, that's fine. That gets to stay. A to the third, that's fine. That's a positive exponent. But notice B has a negative exponent, so that's no good. We have to make it positive. So when I'm rewriting this or simplifying this, the 5, A to the third, that's fine. That gets to stay as is. But the B has to move to the denominator. And when I move it to the denominator, the exponent becomes positive. Again, we're only moving things with negative exponents. So here, just the B has to move. Looking at the middle one, we'll do these two and then I'll have the video pause so you can try the next 3. Notice we just have one term. It's x to the negative 9th. Well, that has a negative exponent. So right now it's on the numerator of the fraction, so that has to move to the denominator to become positive. So that's going to move down here. It's going to become x to the positive 9th. And looks like there's nothing left up top, right? So we assume that that's a 1. 1 over x to the 9th. Last but not least, this one here, right? On the numerator we have 1. The imaginary exponent for 1 is 1. So 1 to the first is just 1, right? That gets to stay. But here we have n with a negative exponent. That is no good, right? So we have to make it positive. So we have to move it to the numerator. So the 1 gets to stay up there with it. I'm bringing the n up to the top to become positive. So it's n to the third. I'm left with nothing on the denominator. If you want to put a 1 there, you can. But if we think about this, just to clean it up, 1 times n to the third, that's just n to the third. Divided by 1 is just 1. So really our answer is just n to the third. Again, just moving things with negative exponents. So at this point, if the sub could pause the video and let you try the next 3 here, and then we'll resume and I will go over the answers with you. All right, hopefully you had time to work through these problems. So on this first one, right, if you're looking through, right, 4 has a positive exponent, that gets to stay. Oops, C has a negative exponent, that's got to go. B has a positive exponent, that imaginary one, that gets to stay. So if I rewrite this, it'd be 4B over C to the third, right? It has to go downstairs to become positive. Looking at the next one. I have 2 over a to the negative third. Well, 2 again has a positive exponent, so that gets to stay. The a, though, does not, so that has to move. It's on the denominator currently, so to become positive, it has to come up to the numerator with the 2. So the 2 stays. A to the third comes up to be, a to the negative third gets to come upstairs to become positive. So it comes up to the numerator with the 2, and it becomes a to the third. Looking at the next one, I like to just circle things with negative exponents. So the n has a negative exponent, the m is fine. So that means the n has to come downstairs to join the m. So that means the m squared stays where it's on the denominator, right? Because it doesn't have a negative exponent. The n has to come join it in the denominator, and it becomes positive. Nothing left on the numerator, so we got to do a placeholder of 1. Hopefully those went okay for you. All right, just 3 slides left here. Sometimes I'm going to be asking you to evaluate the expression, and I'm going to say when certain variables equal value. So when s equals 2 and t equals -3. So we're just doing substitution, which we've done a lot of that before, right? We're substituting 2 in for s and -3 in for t. Here's a little hint on this problem, though. Before I do that, I would look through and I would simplify it just like I was doing previously on the other examples. Before I plug things in, I think that makes things so much easier. So as I go through, I look, and it looks like I have 3, right? That would be raised to the first power, so the 3 gets to stay. S to the third, that's a positive exponent, so that doesn't have to go, right? That gets to stay. But then I have t to the -2nd, right? That's a negative exponent, so that has to move to the denominator. So before I plug things in, again, I'm simplifying. I'd have 3 s to the third over, this would be t to the now positive second. So now I can go ahead and plug in what s and t are, just using substitution. Just like before, whenever I plug something in, I always put in parentheses. So it's 3 s, which is 2 to the third, over t, which is -3 to the second. From here we simplify just using PEMDAS. So if I'm using PEMDAS here, remember we got to deal with our exponents first. And we're going to do kind of our numerator and denominator separately here to start. So on the numerator, I have an exponent, 2 to the third. Well, 2 to the third is 8. So I have 3 times 8 over, and I can simplify this denominator part if I want. -3 squared, that's -3 times itself twice. -3 times -3 should give me a +9. So I still got to clean up the numerator, right? I got to deal with that 8 times 3. Well, that's going to give me 24 over 9. And then I just finish it off, right? 24 divided by 9. Unfortunately, does not divide nicely. But we can simplify, right? Because 24 and 9 both divide 3. Just to simplify. So it looks like I get 8 over 3. Again, just simplifying using PEMDAS. Again, I think it's important to simplify first before we plug values in. I just want to do one more together. I know I'm getting a little long on the video, so I want to give you some work time here and some time to practice. So let's just do one more together, and then I got a word problem, then we'll call it for today. So if we just look at this first one, again, we have to evaluate, says this expression, when n equals -2 and w equals 5. So those are the values we're going to have to plug in. Again, I said I like to simplify before I actually plug values into my expression. So again, if I'm looking through here, I notice I have n with a negative exponent, right? That's the only one that has a negative exponent. So that's the only one that has to move. Currently, it's on the numerator of our fraction, so that's got to go to the denominator. So w to the 0, that gets to stay, over, well, now n moves downstairs to the denominator and gets a positive exponent. I can also simplify something else, right? Hopefully you see that w to the 0. Well, what's anything to the 0 power? Hopefully you're thinking, oh, it's 1, right? So really, I can just replace this. Oops, not with my highlighter. I can replace this with 1 over n to the 4th. So I go ahead and I plug in what n is, right? 1 over parentheses, whenever I plug something in to the 4th power. So I'm going to plug in a -2. So that's -2 times itself 4 times. which if you do that out, you should get 16. Again, you could also type it into your calculator. You have to make sure you put the parentheses there, though. Otherwise, your calculator is going to give you a different answer. It's because the calculator is too smart and it does PEMDAS, and we've talked about that before. So please put the parentheses there. All right, last slide here, and then you can get some practice on the worksheet. So here it says a population of marine bacteria doubles every hour under controlled laboratory conditions. The number of bacteria is modeled by this expression, 1,000 times 2 to the h. It says h is the number of hours after a scientist measures the population size. It says evaluate the expression h equals 0 and h equals -3 for h equals 0 and h equals -3. What does the value of the expression represent in this situation? So they're just wanting us to plug in 0 for h and -3 for h and just kind of evaluating those results. Again, h represents the number of hours after the scientist measures the population size. So we just take our expression here, the 1,000 times 2 to the h. Well, in this case, they first said, well, make h 0. So if I simplify using PEMDAS again, right? PEMDAS says I got to do exponents before I multiply. So I get 1,000 times 2 to the 0. Well, 2 to the 0, that's just 1. So I get 1,000. And what are we talking about here? We're talking about bacteria. So if we think about what this means in the context of our problem, right? It says at time 0 or at hour 0, we have 1,000 bacteria. Well, at hour 0, this would be like at the start of our experiment, right? At the start of our experiment, when we started counting the bacteria at time 0, we would have started with 1,000 bacteria. Now it says, well, go ahead and evaluate when h is -3. So again, we're just plugging stuff in and just interpreting those results. So again, it's 1,000 times 2 to the h. Well, in this case, they're saying, well, make h -3. So I got to clean things up. Again, it's still PEMDAS, which tells me I got to do the exponents first. But we still have to use our exponent rules. We can't just evaluate 2 to the -3 as is, right? We have to make it positive because it has a negative exponent. So the 2 to the -3, that has to move. The 1,000 gets to stay because that's raised to the 1 power. So we'd have 1,000 over 2 to the -3. Well, that's going to become 2 to the +3 power. It has to become positive, so it has to move downstairs to do so. So then I can go ahead and clean things up. I get 1,000 still in the numerator over 2 to the 3rd. Well, 2 to the 3rd gives me 8. And then 1,000 divided by 8. If you plug that into your calculator, you should get 125. So 125 bacteria. And again, if we think about this, well, if the hour time is -3, well, if we think about this, if our experiment starts at time 0, right, that's when we first count the bacteria, this means that if h is -3, this means that 3 hours before I started counting the bacteria, right, based on trends and patterns, I can say that there's probably about 125 bacteria. And we're going to do a lot more with exponential equations, talking about growth and decay. They're pretty handy because they allow us to kind of do some predictions or estimate what values were prior to maybe when we started counting something, or we can use them to, like I said before, predict things that are going to happen in the future. So hopefully this video felt like a little bit of review for you and made sense. As always, you got to make sure, since I'm not here, you got to make sure you reach out with an email if you're confused by anything. The sub will now hand out the worksheet to you. As always, the odds are posted on Canvas, so if you want to kind of check your work as you go, feel free to do so. But also make sure, again, if you have questions, make sure you shoot me an email. Thanks, everybody.